So in our last few lessons, we've gotten a chance to work with some, they're not easy, but they're basic related rates problems. And in today's lesson, we're going to look at one sort of a little bit more advanced geometric example, which turns out actually isn't going to be all that advanced. And then the other thing we're going to do is we're going to look at some direct applications to some science scenarios. And I'm actually going to do those the other way around. We're going to talk about the science things first, and then we'll get to this geometric example of a cone. So before we do that, let's go ahead and take a deep breath. And let's begin. We've got this. All right, so I want to talk briefly about chemistry. Now, if the word chemistry brings up all kinds of like scared and worried memories, don't worry about it. I'm not going to go super deep into all of this. In fact, I barely know the chemistry that I'm talking about here, but I've always thought that this would be a neat application for related rates, so I wanted to share it with you guys. So in chemistry, hopefully remember that there was a thing called the ideal gas law. And the ideal gas law basically just said that that if you've got a gas, that there's a pressure for the gas, there's an amount of volume, sort of space that the gas takes up, there's a number of moles, which gives you like a number of like molecules of the gas that you have, and then there's a temperature, right? And those four things are related to one another by this formula right here, where R is called the ideal gas constant. And now that we're in a lesson about related rates, this word constant is more important to us. And here it is. This ideal gas constant is 0.0821. Okay. Now, I'm really not going to worry too much about units here. I promise all the units work out fine. I just sort of want to look at this, right? So the idea is, if you know the pressure and the volume of a gas, you can multiply those together. And that should equal the number of moles of the gas, sort of like the absolute amount of it that's there, times the ideal gas constant, and then times the temperature. Okay, so if we know all of these things, or for instance, if we know the volume and the number of moles and the temperature, and of course we know the constant, we could compute what the pressure is, right? But I think the thing that I want to get at is real world situations are rarely static. It's not super common that the pressure is staying the same and the volume is staying the same and the temperature is staying the same and everything is just staying the same. It makes for nice, simple chemistry problems, but when we're interacting with things in the real world, things are going to be changing. Maybe the temperature is rising. Maybe the pressure is changing. Maybe more gas is being inputted to the thing. Maybe the volume is increasing or decreasing. So I want to sort of share with you that related rates can be used to see how quickly some of these quantities are changing relative to another one. Okay, so the first thing I'm going to do here is I want us to sort of imagine the most complicated of situations, and then the example we're going to do is going to be easier than this, right? So imagine a situation where the pressure and the volume and the number of moles and the temperature, imagine that all of them are changing. So this is a system that's completely in flux. What would I get if I took the derivative of this thing with respect to t? So when I say that P, V, N, and T are all changing, it basically means P, V, N, and T would all be variables. So if these were all variables, how would I take the derivative of the left side with respect to T? Well, it's the product rule, right? I would do the derivative of the first thing. That would be dP dt times V. So how fast the pressure is changing times the volume, plus this time I'd leave the pressure alone, and I would do the derivative of volume, dV dt, how fast the volume is changing. That should equal, now R is a constant, so I'm going to use the constant multiple rule. I'm going to ignore that R and leave it up front. Okay, and then I need to do the product rule for the N and the T, right? I would do the derivative of the first thing, dN dt, for how fast the number of moles is changing, times T, that's the temperature, and then chain rule, plus constant multiple rule. We still have the R there, but this time I'm going to leave the N alone, and I'm going to multiply by the rate of change of the temperature. Now, I promise, this is not like a formula that you're supposed to memorize, like, oh, this is the derivative of the ideal gas law, ha ha ha. Like, we don't memorize these things. What we do is we say, I know the ideal gas law, which means I can use the process of related rates to basically put the ideal gas law into motion and to get a sense for how these quantities would interact with one another if they were actually changing. Okay, so I sort of just wanted to share with you that even without a deep understanding of chemistry, it's possible for us to take a derivative of this sort of thing with respect to t and then be able to use that in a context. So what I want to do now is I want to sort of actually do an example of a problem that uses this. And again, it's not going to require a ton of knowledge of chemistry. We're really just practicing a calculus thing within a context. So let's go ahead and take a look at that. All right, so in this example, I put in some of the units, but again, I'm really not going to worry about units. I used all of the units here that are supposed to be used standard with this thing, so not something you really need to worry about. So in this example, right, a sealed piston, now what does it mean that it's sealed? Sealed just means that the thing is sort of like closed off. So the piston can go up and down. If you don't know what a piston is, by the way, a piston is like sort of imagine like a cylinder, right, that has another cylinder that's sort of like snugly fit inside of this thing. And so this inner one can sort of move up and down so that like this section here is sort of like the intersection. And so it's almost like you can imagine like a syringe that sort of has a thing here and then like the little part that sticks out the top of it. I'm not drawing this thing very well, but a syringe is sort of like a sealed piston if you were to sort of close the end off of this thing. Okay, so the thing that's important about a sealed piston is that because it's sealed, we can't change the number of moles of gas. You can't change the number of molecules of gas that are in there because it's sealed off, right? So the sealed piston is filled with 5 moles of gas. At the moment, when the temperature is 27 degrees Kelvin and the volume is 4 liters and the pressure is 1.47 atmospheres, the temperature is increasing at this rate, 0.57 degrees Kelvin per second, and the volume is increasing at this rate, 0.076 liters per second. Okay. Now, again, I'm writing the ideal gas law in here in case you forgot it or you don't remember it from chemistry. Maybe you didn't take chemistry. That's okay. We'll forgive you. So recall that the ideal gas law states that PV equals nRT, and R is this thing called the ideal gas constant. Okay. So the first question I'm going to ask is real simple. Not even much calculus here. Of the letters P, V, I'm sorry, that shouldn't be an R. This should be an N. So of the letters P, V, little n, R, and T, which of those are constant and which of them are variable? Well, the things that we know are constant. The things that are constant are R, because it's literally the ideal gas constant, and also N, because this is a sealed piston, and we know that the number of moles can't change. Okay? On the other hand, the things that are variable in this problem, the things that are variable are the pressure, the volume, and the temperature. Okay? So part B is now going to ask us, okay, so hence, take the derivative of PV equals nRT with respect to time. Right? And so I would encourage you to pause the video here and remember, keep track of what's constant and what's variable. Because if something is constant, I don't need to do the dn, like it's a constant. I can sort of ignore that part for the purposes of taking the derivative. So go take a moment to take the derivative with respect to time, with respect to little t. The first thing here is going to be the product rule for us. So this is dp dt times v plus, this time we leave the pressure alone, p times dv dt equals, now on the other side, n and r are both constant. So I'm going to use our derivative constant multiple rule to ignore the n and the r. And then I just need to do the derivative of t, which is dt dt, which is, maybe frustrating use of variables, but whatever, it is where we are. And great, so this is it. This is the answer for part B. This is the ideal gas law compensating for change in the system with respect to time. Okay. Now part C. Part C says, hence, find the rate of change of the pressure of gas in the piston. So of all of the things in this formula, what is it asking us to find or to solve for? It's asking for the rate of change of the pressure. So dp dt is the thing I want to solve for. So dp dt is what I want to solve for. So everything else I should be plugging in. Do I know what the current volume of the gas is? Yeah, it's 4. Do I know what the current pressure is? Pressure, there it is, 1.47. Do I know what the current rate of change of the volume is? Yeah, it says right here, the volume is increasing at a rate of 0.076. Do I know what N is? Yeah, N is the number of moles. Do I know what R is? Sure, R is the ideal gas constant, 0.0821. And do I know what dT dt is? Yeah, it says the temperature is increasing at this rate, 0.57 degrees Kelvin per second. And so we did this sort of heavy lifting of doing this weird derivative, and then the next step was just recognizing, hey, cool, I can just plug in the numbers and solve for this thing, right? Now this is definitely going to require a calculator for us to solve it. All right, so I got here that dp dt, the thing that we want to solve for, that times 4 plus 0.11172 has to equal 0.233985. Right? If I move this thing over to the other side, I get 4 times dp dt is 0.122265. And then the last step is just to divide that by 4. And I got that dp dt is 0.0306. And that's the answer to part C. Right? Part C basically asks us to plug these values in and find what we got. Now part D, is the pressure increasing or decreasing? Right? And explain how we know this. Right? So given that this is positive and the pressure was also positive, the pressure is increasing. Though it doesn't look like it's increasing by very much, 0.03 seems like a small number. With that said, I don't actually quite remember what atmospheres represent, unless atmosphere is like the amount of pressure at like sea level, in which case this would be like only 3% of that pressure, which is maybe not a lot of pressure. Anyway, I'm at the edge of my knowledge of chemistry and the ideal gas law. So I hope that made sense and that you got sort of a chance to see how a formula that we know or maybe have some knowledge of, that formula can be differentiated with respect to time or some other quantity, and we can see how these things change over time. So if you've got questions about those, please write them in your notes or ask me during class. I want to make sure I get a chance to explain that and explain myself. All right, so I've got another one of these science things lined up, and I don't think this one's going to take quite as long. We'll see. This is an application in physics. Some of you may have taken some physics. But again, if you haven't taken any physics, that's okay. I'm going to try and get you through this. So in physics, when you have two resistors with resistance R1 and R2, and you have them connected in parallel, the combined resistance, just R, is found by this formula. Right? Now, all it really means to be connected in parallel is imagine that you have a battery, right? So you've got like a little battery thing here. I think this is the symbol for a battery. Anyway, you got the battery, and the battery goes out and connects to a resistor and then goes back into the battery. If instead you have the wire go up and go into two different resistors that are like, see how they're like parallel to one another? This is what it means to be connected in parallel. The other way that you can connect things is called connecting them in series. So again, if this is the battery thing and you connect it to one resistor and then you connect it to another one, this is called connecting in series. And this is called connecting in parallel. You knowing the difference between series and parallel is literally not important for the IB exam. They're not going to test you on this. This is just me sharing, right? So if you've got two resistors that are, R1 and R2, the combined resistance of the whole thing is found by doing the reciprocal of one plus the reciprocal of the other, and then 1 over that is the combined resistance. Okay? So the question I want to ask now, coming straight into calculus, what relationship would I get if I took the derivative of that with respect to time? So imagine if these resistors were not like static resistors, but they were actually changing. They were like sliding resistors where you could increase or decrease them. So my question is basically, how would you take the derivative, not plus, R1 over R equals 1 over R1 plus 1 over R2. If you wanted to take the derivative of this with respect to t, how would you do it? Well, I would say I would want to rewrite these as -1 powers because it'll be easier to do the derivative. And now I would just go through and take the derivative with respect to t. The derivative of this would be negative r to the -2 times dr dt equals, this would be negative r1 to the -2 dr1 dt. And this last one, same thing, bring the power down, negative r2, subtract 1 from the power, minus 2 dr2 dt. And again, this might look scary because it looks like alphabet soup and stuff, but the reality is that's it. That's the relationship. If this resistor was allowed to change and this resistor was allowed to change, you could use that to find out how much the resistance of the whole system was changing. Right? So let's take this idea and let's see if we can apply it to this example that I have. So imagine that two resistors with resistance R1 being 425 ohms and R2 being 350 ohms are connected in parallel. By the way, that symbol is the capital Greek letter omega, but you pronounce it ohms for the unit in physics, spelled OHM, and it's just kind of like a line and then like a loopy thing and then a little line. They don't need to look super pretty like the font does. So part A, I just kind of want us to check, how could we find the combined resistance of the circuit, right? Well, the formula was supposed to be 1 over R equals 1 over R1 plus 1 over R2. So to find the combined resistance, all you would need to do is simplify this relationship. Oops, this was 425. Sorry about that. So, I mean, I would say pause the video for a moment, make sure that you're comfortable like using a calculator to simplify this and figure out what it is. So to do this, if I do 1 over 425 plus 1 over 350, I get that 1 over R is 0.00521 blah, blah, blah. I would need to do the reciprocal of that, and I find, okay, the combined resistance of this system is 192 ohms. Okay, it's actually 191.935, blah, blah, blah. This is correct to 3 significant figures. Okay, so this is the answer for part A. Now, the problem says if the resistance of the first resistor is decreasing at this rate, and the second resistor is increasing at this rate, what is the rate of change of the combined resistance of the circuit? Okay, so in order to do this, what I'm going to need to do is I'm going to need to take my relationship, this 1 over R plus 1 over R. Man, I keep doing that. It's not plus, it's equals. Equals 1 over R1 plus 1 over R2. And then I'm going to do the derivative. I'm going to take the derivative of this with respect to t, just like we did in the previous slide. That was negative r to the negative 2 dr dt equals negative r1 to the negative 2 dr1 dt. And I just can't write today. I'm having trouble. Minus r2 to the negative 2 dr2 dt. And now that I have this thing, I can go through and I can plug in the values that I have. Now remember, what's it asking for? It's asking for the rate of change of the combined resistance. In this formula down here, where do you see the rate of change of the combined resistance? It's this right here. All the rest of this stuff is stuff that I'm going to need to plug in. So let's go back and see what we know. Do I know what the combined resistance is? Yeah, I found that out on the earlier problem. This would be negative 190, and it's whatever it was. It was 191.935, blah, blah, blah. That whole thing squared times the dr dt that I'm trying to solve for equals negative r1 squared. So that would be 425 squared times the rate of change of the first resistor. Well, the first resistor is decreasing at negative 1 ohm per second. And then minus the second resistor was 350 squared. I'm sorry, not squared. It's actually to the negative 2, isn't it? All these are to the negative 2 power. And then the dr2, the second resistor is increasing at a rate of 1. So this would be positive 1 over here. Okay? And at this point, I'm just going through and sort of confirming values here. I'm punching things into the calculator. I've got this 425 raised to the negative 2. Oops. 425 raised to the negative 2 power. So this is some really, really tiny number. In fact, it's so tiny that the calculator is actually giving it in scientific notation. This is 5.54 times 10 to the negative 6th, and then minus 350 raised to the negative 2. This is 8.16 times 10 to the negative 6th. And on the other side of the thing, I have this negative 2.714 times 10 to the negative 5th dr dt. And this seems really ugly, but remember, you've been using your calculator for this, so you can really just take stored values and subtract these things. Like I'm going up and taking that 5.53 and then subtracting that 8.16 number, right? And then I'm going to divide that by the opposite of the answer that I had gotten here, this negative value here. And when I do that, I'm getting that dr dt is positive 0.0968. Right? And so we can see that even if it's only very slightly, the overall resistance of this whole circuit is increasing because dr dt is positive. Maybe take a deep breath here. There's a lot of variables. There's a lot of science knowledge running around here. Some of you are excited to see this, and some of you are like terrified because you were hoping that math was just going to stay math. Problems like these are not super likely to show up on the IB exam. They might show up there. I think I really wanted you guys to know that this is a way that calculus can be used. And so I want it to be something that you guys got a chance to see. The rest of this is not going to be science. So we're going to do one example of one other geometric type problem. So it's going to be a rather different topic, but I want to go over and take a look at that now. So let's go give that a shot. All right. So the last thing we're talking about today, one type of slightly more complicated geometric related rates problems is about a cone. Okay. So recall, or maybe I'm teaching you right now, the formula for the volume of a cone is 1/3 pi r squared h. Okay, where h is the height of the cone. So you imagine that you've got a cone like this, right? Like it's an ice cream cone, right? The height of the cone is this vertical height, from the point of the cone to the center of the base of the cone. Okay, so that's the height. And then the radius is just the radius of the circular base of the cone. Okay, now the thing that is going to make this problem a little bit more complicated for us is that there are multiple variables here. Okay, but ultimately this problem is going to end up being quite similar to other ones that we've done where multiple variables are involved. We just need to bring in some other, like some ratio or some relationship between these two variables. And the thing that I'm going to point out to you is that the ratio between the radius and the height is always going to be the same throughout these problems, right? So if you're told in the problem that the radius is 2 and that the height is 4, it doesn't matter where you are in this thing. If you're partway through the cone or just at the very beginning of the cone or you have all of the ice cream left, the ratio of the radius to the height will always be equal to sort of like the overall ratio of the things, right? And so because of that, you can actually solve this thing and then take this relationship and plug it back in over here to get only a single variable. This will make a lot more sense as we do an example. So let's go ahead and get into that example now. So imagine that you have an inverted conical water tower. What does that mean? Inverted conical water tower. So this just means that you've got like a water tower that's in the shape of a cone and that cone is upside down. Now you might be thinking, wait a minute, that cone's not upside down. That's how an ice cream cone is supposed to be. I mean, it's fair. But in math, we often think of cones as the base being on the bottom and the pointy part being on the top. And so often we'll refer to this as an inverted cone, effectively because it's set upside down. Okay, so you've got this conical water tower that has a height of 10 meters, and it's got a radius of 3 meters. And it says that the tower is being filled with water, so you've got this water level, and the water is being filled, the water is being poured into this thing at a rate of 4 cubic meters per hour. Okay, and so this rate would be a dV dt. This is the rate of change of the volume of basically of the cone of water that's in this thing. So it's not that the whole cone is changing, it's that, I should use blue for it, it's that the nice, clear, refreshing blue water in the bottom of the cone is also a cone shape, and as I fill that in, that cone is getting bigger and bigger and bigger. And so the first question that I'm going to ask here is, how quickly is the water level in the tower rising when the depth of the water in the tank is 2 meters? How quickly is the water level in the tower rising? In other words, how fast is the water level going up? Is that an R thing or is that an H thing? Like, what kind of rate is that? Isn't that a dH dt kind of thing. Like dH dt is the thing that they want us to solve for. Okay? So now, just like we've practiced in these problems, they gave us a rate for the volume. We want to find a rate for the height. And so I need a formula that's going to link these two things together. My formula is going to be 1/3 pi r squared h. Now my only complaint here is that I would rather not have the r here. If I take the derivative right now, I'm going to have a dr dt, and I don't know what dr dt is. That kind of sounds messy, so I'd rather not do that. If only there was some way I could replace this r. It would be so great if I knew something about how r was related to h. And I can't just plug in that r is 3 because the radius of the water here is changing. As the water gets deeper and deeper, the radius of this cone of water gets bigger and bigger. But what I mentioned on the previous slide is that the relationship between the radius and the height, the relationship between those two things will always match the overall cone. In other words, r will be 3/10 h. And so I can take that and I can plug it in here. So when I do that, I'm going to get v is 1/3 pi times 9/100 h squared times h. That was just me squaring 3/10 and then the h. The 9 and the 3 will cancel down to 3, so it looks like my volume formula is 3 pi over 100 times h cubed. Now I have a relationship that's just in terms of v and h, and I can take the derivative with respect to t. Okay, so taking the derivative with respect to t, I'm going to get that dv dt is, if I bring the 3 down, 9 pi over 100 h squared times dh dt. Okay. And at this point, I can plug in all the stuff that I know. Okay, dv dt is 4. 9 pi over 100, we already knew. H, for us, it said how quickly is the water level in the tower rising when the depth is 2 meters. Okay, so that means the current depth is 2, and then dH dt is what I want to solve for. Okay, if we actually go on and solve this, we find that dH dt is 100 over 9 pi, which is, let's see here, 100 divided by 9 pi, 3.54. And this looks like it would be measured in meters per hour. Okay, so that's my answer for this one. Now, part B is actually a really, really quick question because it's the same question with a different number. How quickly is the water level in the tank rising when the depth of the water in the tank is 6 meters? Do you recognize that this is going to be the exact same computation. It's just that dv dt is still 4. This is 9 pi over 100, but now this is 6 squared, not 2 squared, and dH dt. And so when I multiply all of this out and divide it over, I'm going to get that dH dt is 0.0982 meters per hour. And then the very final question, this is the last question of the video, last question of the lesson. What do you notice about the difference in those rates? And why does that difference make sense in this context? Right? What I hope you've noticed is that when the water tower wasn't very full, when it was filling up sort of the bottom part, it was going up at like 3.5 meters per hour. And then once the thing was like halfway full, now it's only going up at like 1/10 of a meter per hour. Why is it so much slower now? And the answer is, and you've probably experienced this before, when you're filling something up, if the bottom of the cup is really small, it's going to fill up fast because there's not much room down there. Whereas when you're getting up near the top, it takes a long time to fill this up because there's so much more area that's available for water to fill in up there. So that's sort of why this answer makes sense. So I hope that lesson as a whole made sense. This is the last lesson that we're having on related rates. After this, we're going to move on and practice another thing with our derivatives. But as always, if you guys have questions on these things, please let me know. I'd love to help clarify it. So best of luck as you work through these exercises.